So last time we introduced this idea of quadratic reciprocity, and we're going to return to this today. So remember, this concerns, so remember, we're dealing with quadratic residues. Something's a quadratic residue if it is a square in that modular system. So it's a quadratic residue modulo P. If it is a square, another way of saying it, if it has a square root. We have this object called the Legendre symbol, just like a piece of notation. So the Legendre symbol NP, this is the value +1 if n is a quadratic residue, and -1 if it is not a quadratic residue. It's just like an indicator function. It indicates, it's just a way of, it just represents +1 if it is a square, -1 if it is not a square. And a couple of the results we looked at last time were concerned with working with this Legendre symbol and starting to gather results about how it behaves. Okay. Two important things we looked at. Well, clearly, if something looks like a square, so m squared, of course, is a square. It's the square of m or minus m. You can tell that straight away. So if something is obviously a square, of course, it has the value +1. It is a quadratic residue. Another property, now we proved this a couple of weeks ago when we first started discussing quadratic residues, this symbol is multiplicative as well. Okay? So if you evaluate the Legendre symbol on a product NM, it is very nicely the product of the individual Legendre symbols. Okay? So it's a very nice property to have. Since we're in this multiplicative group of congruence classes modulo P, we've got this interesting phenomenon of being a square or not being a square. It's all about multiplication. So it's very nice that our indicator function is multiplicative. Evaluated on a product, it's just the product of the individual symbols. Okay? This is the corresponding property to linear. If you're in an additive situation, like a vector space, some kind of system where you've got an addition-like operation, then you want things to be linear, your functions. When you evaluate a function in a sum, it's very nice if that is just the sum of the individual function values evaluated on the terms of the sum. Here we have the corresponding property for multiplication. So the Legendre symbol is yes. So sorry. In this number theory sense, multiplicative. This only works if the it doesn't. It is completely multiplicative. Any product. Sorry, I was worrying there that n and m have to be co-prime. No, they don't. Any n and m in there at all, and it splits up. So this is reviewing last time. So we had this Euler's criterion. So these are different ways we're coming at evaluating the Legendre symbol. Euler's criterion, we found that this value, ±1, which is represented here, is congruent to the value you get when you raise n to the power of p minus 1 over 2. Okay, we proved that last time. And this Euler's criterion is kind of the basis for the rest of the work we do with the Legendre symbol, really. So taking that formula, that n, the Legendre symbol np, is congruent to n to the power of p minus 1 over 2, we were able to very quickly describe the Legendre symbol values for -1. So this result here, we proved a couple of days ago, a couple of lectures ago. The Legendre symbol -1p is +1 if p is congruent to 1 mod 4, -1 if p is congruent to 3 mod 4. Every prime number after 2, of course, is odd. So it's either congruent to 1 or 3 modulo 4. And this result, we understand completely now when -1 is a quadratic residue modulo p and when it isn't. Just depends on the status of p modulo 4. That's a very nice result. Based on Euler's criterion, a slightly longer proof was required for establishing this result, which we did last time, which is a similar result for 2. So when is 2 a quadratic residue? When is it not? This is based on the status of p modulo 8. Every prime number after 2, of course, it's odd. It's an odd number, so it can only be congruent to 1, 3, 5, or 7 modulo 8. So 1, 3, 5, and 7, or you can think of that as ±1 and ±2. And this is how it broke down. That 2 was a quadratic residue if p was ±1 mod 8, p was 1 or 7 mod 8, and not a quadratic residue, minus 1 for the Legendre symbol if P is plus or minus 3. Now, I'm jumping around these results a bit because I want to show you some example calculations. In a few moments, I'll describe a method now which will allow us to evaluate the Legendre symbol for any argument. Okay. So far, we've only seen these nice results for minus 1 and 2. But I'm going to give us some kind of procedure. It's kind of, you know, it feels a little bit like the Euclidean algorithm. It's a kind of a repetitive process where the arguments decrease all the time until eventually they get so small that you can just tell what the answer is straight away. Just like when you're working out the GCD of large numbers, you keep doing those integer divisions. Eventually, you get very small numbers, and you can see what the greatest common divisor is. But now this technique is based on this idea of quadratic reciprocity, which we finished off by just looking at the statement of it last time. Now we're going to, in the remaining lectures, we're going to be working up to a proof of quadratic reciprocity. So this is the law of quadratic reciprocity. So P and Q are distinct primes. And what this is doing, you see, it's relating the Legendre symbol QP to the Legendre symbol PQ. So QP takes a value plus or minus 1, which indicates whether or not the congruence class represented by Q is a quadratic residue modulo P. So whether Q is a square modulo P. PQ is the Legendre symbol that refers to the other constant. Whether or not P this time is a quadratic residue modulo Q. Now, the surprising thing about this result is, as we said yesterday, or said the last day, that the multiplicative system of congruence classes modulo P, you know, is quite different to the multiplicative system modulo Q. They're two different primes. They're different groups of different size, and there's, you know, from what we've seen up to now, there's no reason for us to expect there to be nice structural relationships between the two groups. Okay. Now remember, in any one of these multiplicative modular groups, half of the elements are quadratic residues and half of them aren't. Okay. So if it was all completely random, half of the time you'd expect QP to be plus 1, half of the time you'd expect it to be minus 1. And on the other hand, half of the time you'd expect PQ to be plus 1, half of the time PQ to be minus 1. So if there was absolutely no connection between the systems, modulo P, modulo Q, we'd only expect the Legendre symbols to agree 1/4 of the time. Because each of them has two possibilities, plus 1 or minus 1, the other one plus 1 or minus 1. So if there was no systematic connection between them, you'd only expect them to take on the same value as each other 1/4 of the time. But this result says that it happens 3/4 of the time. Okay, so it's when they agree and when they don't agree is completely trivial to understand. It's just based on the status of primes modulo 4. The quadratic reciprocity says that the Legendre symbol QP is equal to the Legendre symbol PQ in every case except when both the primes P and Q are congruent to 3 mod 4. And that's a very easy check. You just divide the prime, even if it's a huge prime, just divide it by 3. Do that very quickly. Sorry, divide it by 4. Do that very quickly and check whether you've got a remainder of 3 or not. You'll either have a remainder of 1 or 3. If both of them are congruent to 3 modulo 4, then the Legendre symbols take opposite sign. So QP is equal to minus PQ. Okay. Now this is our, the most complicated result, the hardest result to prove in the whole course. Naturally enough, it's what we're going to finish with. But before we embark on the kind of journey to prove it, let's see some examples of it being used. Okay. So this is if we look in our notes on page, well, you don't have to look at it. Page 64. There's a little worked example. So let's have a look at this. Or any questions about before we jump into the example? Any questions you'd like me to clarify? Okay. So this problem. Example 8.3. This is an application of quadratic reciprocity. So the basic question, I guess, lying behind this is: are there solutions to x squared being congruent to the numbers here are 219 modulo 383. So choosing some medium-high numbers to work with. 383 is a prime. 219 is it. Now, okay, so this is the question: is 219 a quadratic residue? Is there an x such that when you square it, you get to 219? We don't know. 219 is not a square integer in the normal sense. It doesn't have an integer square root in integer arithmetic, but in modular arithmetic, it might have. So how do we discover that? Okay. So we need to evaluate. We need to evaluate the Legendre symbol 219, 383. We need to work out whether this is plus 1 or minus 1. If it's plus 1, then there are solutions. If it's minus 1, then there aren't. It won't help us find the solutions. To find the solutions is harder then. You basically just have to go through a trial and error check, maybe. Or find the square roots of all its factors, some of its factors, and then multiply them together. Now, so I said this was, in some senses, this feels a little bit like the Euclidean algorithm, in that we were trying to evaluate something for large arguments. So the Euclidean algorithm, we were trying to work out the GCD of two large numbers. Euclidean algorithm sends you on a repetitive process of integer divisions with remainder. And the numbers are getting smaller all the time. The GCD is remaining fixed all the time. And eventually you've got really small numbers and you can just read off the GCD. So you've got the GCD of something with 0. That has to be something. Similar overall framework here. We want to evaluate this Legendre symbol. It's got large arguments. We don't want to do it by trial and error, trying all the congruence classes modulo 383, squaring them all, seeing if we get 219. We don't want to do that. We want to do it in a cleverer way, or a kind of a way which makes more use of the structure. So what we're going to do is we're going to pass through a sequence of equations involving Legendre symbols, but the arguments are going to be getting smaller all the time. So the first thing we're going to do is we're going to use the multiplicative property. We're going to factorize 219. So how does 219 factorize? By spot a small factor of 219? 3. 3 and something, yeah. 3 goes into 21 and 3 goes into 19 as well, or into 9. So yeah, 3 and 73. So we know the Legendre symbol is multiplicative. That's one of the results we reminded ourselves in the introduction. So this Legendre symbol is definitely the product of these two. Okay. Now, so that's by using multiplicative property. Property that allows you to factorize the Legendre symbol in the first position. And now we'll use quadratic reciprocity to flip each of these. See, 3 is a prime and 73 is a prime. Okay, that's important. If you had a large number here which wasn't a prime, you just keep factorizing it. So what we want to do is factorize the original Legendre symbol to a product of Legendre symbols where all the first arguments are prime numbers. And then we can use quadratic reciprocity to flip it. So what we're going to do is we're going to relate the Legendre symbol 383, to the flipped one, 383. 3. Now, is it the same value or is it the opposite value? Well, the law of quadratic reciprocity says you just have to check the status of both of the primes modulo 4. Now, 3 is congruent to 3 modulo 4. What is 383? Just divide it by 4, look at the remainder. 4 goes into 38 9 times. Is it 36? Remainder 2. And 4 into 23 goes 5 times. 20, remainder 3. So yeah, both of them are congruent to 3 modulo 4. So that means the Legendre symbol is minus the Legendre symbol 383 is minus the Legendre symbol 383. This one, okay, 383 is congruent to 3, so we just have to check 72. Divided by 4 goes in once, remainder 3. 4 into 33 goes 8, remainder 1. Okay, so 73 is not congruent to 3 modulo. It's congruent to 1. So the law of quadratic reciprocity says that these two Legendre symbols are equal. So I can just flip the arguments. So this is by QR. Since 3 is congruent to 383, well, they're both congruent to 3 modulo 4. And 73 is congruent to 1. So we can flip the first one, but we have to flip the sign as well, so we multiply it by -1. And we can flip the second one. We don't need an, it has the same sign. Now what do I do? Well, the solution is drawn out of the notes. This Legendre symbol is indicating whether or not 383 is a square modulo 3. Now, if you're in the system modulo 3, you don't want to talk about 383. You want to work out what its standard reduced residue is, don't you? So what is 383 congruent to modulo 3? Because remember, the Legendre symbol, considered as a function on the first argument, is a function on the congruence classes modulo prime. Yeah. So the Legendre symbol of this number modulo 3, well, really it's talking about the congruence class of this modulo 3. So we'd rather have it standard reduced represented, which is 2, I think. So you divide this by 3, 3 goes into 100, 3 into 80 goes, 3 into 8 goes twice remainder 2, and 3 into 23 goes 7 times remainder 2. So congruent to 2. And similarly, reduce 383 modulo 73. And it's going to go misprint in the notes there. It goes down to 18. See there in the notes on line 879. I wrote in 383 again. That second should be 73. Just like it was. So this is using what's going on here. This is using the congruence property. 383 is congruent to 2 modulo 3, and 383 is congruent to 18 modulo 73. Okay, 18 modulo 73, who knows for now, but 2 modulo 3 is 2 a quadratic residue modulo 3. We have to consider that. We can just go back to, just think of the original definition. There's only 3 objects modulo 3. There's only 2 objects modulo 3, 1 and 2. In the multiplicative group, square both of them, you get 1 both times. Because 2 is congruent to -1, so when you square 2, you get 1. So yeah, 2 is not a quadratic residue modulo 3. So this is equal to minus -1. -1 gives you this value here. 1873. So we're left with just 1873. So our original question was, is 219 a residue modulo 383? We've now reduced it to the question, is 18 a residue modulo 73? Okay, this is a much simpler question because the arguments are smaller. So just like in the Euclidean algorithm, you have this kind of process to go through where you're using various properties and you're reducing the arguments. Now, I'm not going to answer this question, is 18 a quadratic residue modulo 73? I'm not going to answer that directly. I'm going to go through the whole process again. So I factorize 18. Or first of all, any questions, any queries? Yeah.
By QR.
Yeah.
73 congruent to 1 modulo 4.
Yes.
I just don't get that.
So remember, quadratic reciprocity said that the 2 Legendre symbols, QP is equal to PQ, unless both of the inputs, both of the primes, are congruent to 3 mod 4. If they are, you have to introduce a minus sign because they have opposite states. This is a residue. Q is a residue modulo P, then P is not a residue modulo Q, and vice versa. Okay. So basically, the idea is when you meet these Legendre symbols, both of the arguments are prime, you can flip them. But if both of the primes are congruent to 3 modulo 4, you need an extra minus sign. So when I was working through it, I had 383. Both of them are congruent to 3 modulo 4. Both of those primes. So when I flip it, I need to introduce a minus sign. 73, 383, they're both primes, but 73 is not congruent to 3 modulo. It's congruent to 1. So the law of quadratic reciprocity, which we haven't proved yet, but we're going to be building up to the proof of it in the remaining lectures. That tells us that we can flip that Legendre symbol without bringing in an extra minus. And the flipping is where the reduction in size happens. Because when you have your first Legendre symbol, you factorize it, so you've got small number modulo a large number. But when you flip it then, you've got large number modulo a smaller number, and then the next stage is you're reducing the large number modulo the smaller number. So that's where the things are getting pushed down, squashed down. So is 219 a quadratic residue modulo 383? That has the same answer as is 18 quadratic residue modulo 73. So we keep going. We factorize. 18 is 2 times 9, and 9 is 3 squared. Remember, it's completely multiplicative. So I could have factorized as 2 modulo 73, 9 modulo 73. Then the 9 modulo 73 is just 3 modulo 73 multiplied by 3 modulo 7. Now, do I have to worry about the status of 3 modulo 73? Do I need to investigate that and find out whether 3 is a quadratic residue modulo 73? Should I waste my time and yours by trying to figure out whether this is plus or minus 1 here? Why not?
It's going to be 1 anyway.
It's going to be 1 anyway, because we're going to square it. Yeah. So I can just drop that completely. Remember, the individual Legendre symbol is plus or minus 1. So when you square it, it's just going to be 1. So we've reduced the question to this. Now I could keep going again here. I could flip, reduce, factorize. Well, I wouldn't be factorizing because it would just flip to either. Well, there has to be one modulo 2. But you see, we've already proved everything about 2, haven't we? Remember, the proof last time gave us our result for 2. The answer to 2 modulo any prime is plus or minus 1, depending on the congruence class of P modulo 8. So we just have to check 73 modulo 8. Of course, 73 is congruent to 1 modulo 8, isn't it? 1 modulo 8. So if it's 1 modulo 8, then this is equal to plus 1. So this is theorem, what was that? Theorem 8.6. Since 73 is congruent to 1 modulo 8. So we get the answer plus 1. So 219 is a quadratic residue modulo 383. So it has square roots. There are a couple of square roots floating out around there. I'm no wiser as to what they are at the moment, but I know that they are. Can you kind of see how it feels a little bit like the Euclidean algorithm? You know, you're doing some repetitive steps on the arguments, and they're reducing in size until they get so small. One of them is 2. We've already proved completely, you know, everything about 2 by theorem 8.6. Yeah, so the remaining lectures then are working towards a proof of quadratic reciprocity. So let's take another one of these examples, because I think this week's 7, 8, 9. Yeah, we've got enough. Actually, I won't push ahead through the theorems, but there's a couple of results, a couple of kind of staging results we need to go through before we can prove quadratic reciprocity. So we'll begin those next week. So let's look at another one of these examples. If you look on page 68, here. Let's choose one of these. Let's say go 400. Let's choose this one. 461 modulo 773. Are there solutions to x squared being congruent to 461 modulo 773? So 773 is a prime. So we want to evaluate 461 modulo 773. So the first stage would be to factorize. Yeah, 461. I'm a bit unprepared. What's the factorization of 461? Not divisible by 2. 3 goes in once. Made a 1. Not divisible by 3. 4, 5, 6, 7 maybe. 7 into 46 goes 6 times 7 is 42 minus 4. No, not divisible by 7. Divisible by 9. Someone factorize this in their phone or something. Anybody got it? Or is it a prime? Maybe it's a prime. It's prime. Hasn't got a small factor anyway. Yeah, it's prime. Okay. So I think I didn't waste any more time looking for factors of it. It's already prime, so we should use quadratic reciprocity immediately. Let's flip it immediately. We'll flip it, and then we'll think about whether it needs a minus sign. We need to check the status of these things modulo 4. Well, hundreds are divisible by 4, 60 is divisible by 4, 4 times 15. So 461 is congruent to 1 modulo 4. So they're not both congruent to 3. If they were both congruent to 3, I'd need a minus sign here to flip the status, but they're not. So I flip them. Now I've got a large number modulo a small number, so I can reduce the large number. So 773 minus 461, 2, 2 minus 1 is 2, 7 minus 6 is 1, 312. Yeah, so that's using quadratic reciprocity. By QR. Sorry, this first one was by QR. This one is by congruence. And 312, my computer tells me, is 2 cubed, 3 by 13, I think. 2 cubed by 3 by 13. So I get 2 modulo 461 cubed times 3 modulo 461 times 13 modulo 461. So that's by factorizing. Now I do have to worry about the status of this here because it's cubed, so it could be minus 1. Okay, but I've got my theorem 8.6, so I just have to check the status of 461 modulo 8. So checking that, 8 goes in 5 times omega 6. 8 into 61 goes 7 times omega 5. Sometimes 8 is 56. So yeah, so 461 is congruent to 5 modulo 8. That's minus 3. So that means 2461 is minus 1. It's not a quadratic residue. Well, 3461 I'm just going to flip immediately using quadratic reciprocity, and 461 modulo 13 I'm going to flip in quadratic reciprocity. Remember, I've already checked. We checked 461 is congruent to 1 modulo 4. So since that's involved, I just flip the Legendre symbol. I don't have to worry about checking the other one. So this is minus 1. 461, I just need to reduce that modulo 3. What is it? 1 remainder 1, 5 remainder 1, 9 remainder 2. Seems to be 2. Please check that. 461 is congruent to 2 modulo 3. And then 461 modulo 13. 6. Now, in our previous example, we explained why, well, we observed that 2 is not a quadratic residue modulo 13. So that Legendre symbol is minus 1. So the 2 minus signs are going to cancel. So this is just going to be 613. Which by factorization will be 213 by 313. Two modulo 13, so just have to check 13 modulo 8. Modulo 8, it's 5. One more time, it's 5, which is minus 3, so that's minus 1. But 313, can do quadratic reciprocity again. 13 is congruent to 1 modulo 4, so it flips, and it just, I don't need the extra minus sign. I've got minus sign here, which came from 213. Then reduce 13 modulo 3, it's 1. And is 1 a quadratic residue modulo 3? Is 1 a quadratic residue modulo 3? Yeah. 1 is always a quadratic residue because 1 has the square root 1. Plus or minus 1. So this is minus plus 1. So it's minus 1. So this equation seems to not have solutions. So there are no solutions. To x squared being congruent to 461. So you can see how now the property of quadratic reciprocity is of course crucial to this. This allows you to do the flipping. And the flipping allows you to do the modular reduction, and that's what pushes the arguments down. Takes our large argument symbol down to small argument symbols, which we can evaluate. That's quite a nice process. Should just probably verify this for take it on blind faith. You can see there is plenty of scope for going slightly wrong. You know, you've got minus signs flying around, and you're checking the status of your primes modulo 4 and modulo 8. You know, so there's a kind of, you know, there's plenty of opportunities to slip up there. So I can try checking this just to verify. Doing something else there at matrices, not sure. So what are we doing with this? We're trying to solve the equation x squared equal to, so what was it originally? 461, and the modulus is 773. So I'm hoping I get nothing. An empty solution set. There are no solutions. Okay? If there were solutions to it, it would tell me what they were. Okay. So that confirms the work we've done. What was the other one? 219. The previous example was 219 modulo 219 modulo 383. So I do expect solutions here. I expect 2 of them, plus and minus something. Yeah, so 169 and 214, they're the 2 solutions to, they're the 2 square roots of 219 modulo 383. And they are plus and minus of each other. When you add them together, you should get 383. Yeah, you do indeed. Any questions about that, or about the way we're using quadratic reciprocity? So I didn't put in as much justifications for every step. You see the process. Take your original symbol, factorize it. You factorize it. Basically, you're using the prime factorization of the first argument, factorizing it into a product of powers of primes. So then you have your product of Legendre symbols, and then the first argument is always a prime. If there is a power that crops in somewhere, like 2 cubed was 9 as a factor of 312, you take the cube outside, using the multiplicative property to take the cube outside. Then you got a bunch of Legendre symbols, which is prime modulo another prime. You can use quadratic reciprocity to flip those. Then you've got large number modulo smaller number, so you use the congruence property to shrink the first number. Then you keep repeating. Factorize, flip, reduce. Factorize, flip, reduce. Factorize, flip, reduce. but things are reducing all the time. Eventually they get so small, the answer is just obvious. Or we've got a stored result already, like the result about 2 modulo 13, or status of -1. You can use those results when the arguments get small. Okay. Okay, so we're nearing the end of the course, but there's still a bit of a hill to climb because we want to prove this result of quadratic reciprocity. It's the hardest thing to prove in the whole course. It doesn't have, most of the things we proved up to now, we've been able to kind of give the proof of the result in one lecture or so on. The way I've got for quadratic reciprocity here, the treatment I'm following here, we need to build up a few results towards it. Okay. So we'll commence that next week. Any questions before we end? Okay, so in the tutorial next week, we can do some more work with these at the end of chapter exercises. Yeah, we can try using these ones, applying the Legendre symbol and so on. Okay, thank you for listening, and I'll see you later on.